boundary conditions for the basic equation. The basic equation, there are three basic differential equations of fluid motion which derived in previous videos, where there is a continuity equation in differential form, rho v equals to 0 momentum rho dv on dt and energy. Where phi is a dissipation rate and calculated from the relation in a Newtonian fluid due to the Newton's law of viscosity, which says that the shear stress is proportional to the change of the velocity in each direction, a square plus dissipation rate in the energy equation in a Newtonian fluid motion. In general, the density is variable, so that these three equations contain 5 unknowns, which are in this equation 5 unknown: rho, v, p, internal energy, and T, temperature. Therefore, we need two additional relations to complete the system of equations. These are provided by data or algebraic expression for the state relation of the thermodynamic properties. So we have two relations also for rho, a function of P and T, and internal energy is P and T. For example, for a perfect gas with a constant specific heat, we can compute the relation for rho and, for example, internal energy. Rho is P on RT in a perfect gas assumption, and the internal energy equals to the integration of CV dt equals to CVT plus a constant for a perfect gas. It is shown in advanced book that the system of equations well posed and can be solved analytically or numerically subject to the proper boundary condition. What are the proper boundary conditions? It's the main question in the solving problem in differential equation. What is the proper boundary condition? At first, if the flow is unsteady flow, there must be an initial condition at t equals to 0. We have a rho Vp internal energy and T as a function of a spatial value for the 5 flow properties. Therefore, for all times T to be analyzed, we must know something about the variable at each boundary enclosing the flow. The second boundary condition is for a solid impermeable wall. You write solid. There is no slip and no temperature jump in a viscous heat conducting flow. No temperature jump, no slip condition, which means that the V fluid at the wall boundaries equals to V wall, and the temperature of fluid equals to T wall. The only exception to these boundaries occurs in an extremely rarefied gas flow where the slippage can be present in the appropriate references. Second, at any inlet and outlet section, the complete distribution of velocity, pressure, and temperature must be known for all times. So we have V, P, and T as initial values for inlet and outlet flow. These inlet and outlet section can be and often are at infinity, simulating a body immersed in an infinity expanse of fluid. Finally, the most complex condition occurs at a liquid-gas interface. Boundary condition. of free surface as the interface have the relation z equals to a function of and t. Then there must be equality of vertical velocity across the interface so that no holes appear between liquid and gas. So we have d eta on dt, which is a plus x direction and y direction spatial acceleration. This is called the kinematic boundary condition. There must be mechanical equilibrium across the interface. The viscous shear stresses must balance as the relation at the liquid surface tau yz equals to the shear stress on the gas surface, and also we have a shear stress in the plane zx for liquid equals to the shear stress in the zx plane for gas interface. Neglecting the viscous normal stresses, the pressure must balance at the interface except for the surface tension effects. So we have the relation also for normal pressure at the interface equals to P liquid, P gas, which is equivalent to the equation in the previous section, chapter 1. The radius of the curvature can be written in terms of the resurface position eta. The relations are available in the reference, and finally we have the boundary condition for heat transfer. The heat transfer must be the same on both sides of interface, since no heat can be stored in the infinitesimally thin interface. So we have the relation in the gas-liquid interface for heat transfer. Neglecting radiation, this is equivalent to a relation Fourier relation for the heat transfer at the gas and liquid interface. This is as much detail as we wish to give at this level of exposition. Further and even more complicated detail on fluid flow boundary condition are in the appropriate references related to viscous flow. The next subsection in this section is the simplified free surface condition. In the introductory analysis given in this book, such as open channel flow in chapter 10, we shall back away from the exact condition at previous condition for the gas and liquid interface and assume that the upper fluid is an atmosphere that really exerts pressure on the lower fluid, with shear and heat conduction negligible. We also neglected non-linear term involving the slopes of free surface. We then have a much simpler and linear set of conditions at the surface. We have the boundary condition P liquid, plus to 0, and also a condition for equals to 0. In many cases, such as open channel flow, we can also neglect the surface tension so that P in such open channel flows we have a condition for P liquid equals to P atmosphere. These are the type of approximation that will be used in the later chapter. The non-dimensional form of this condition also will be described in chapter 5. This condition is a special case of liquid-gas interface condition where the gas is atmosphere. Okay, or atmosphere. One type of flow motion also in fluid mechanics is the incompressible flow with constant properties. With constant flow with constant properties such as rho, mu, and K equals to a constant that is the basic simplification of the basic equation of motion and the three basic equations of motion: quantity, momentum, and energy will be reduced to first continuity. In the case of density constant, the density parts vanishes and we have this relation for continuity, and for momentum we have the relation of P plus the PV is a vector for momentum, and energy is the rho Cp equals to the plus phi. Phi is a dissipation rate in energy equation, and the relations are available in the previous video. Energy. Since rho is constant, there are only three unknowns, P, V, and T. So in incompressible flow with constant properties. The rho is constant, as we say before, and there are only three unknowns. P, V, and T. The system is closed. Not only that, the system is split apart. Continuity and momentum are independent of T. Thus, continuity and momentum independent of T. Thus, we can solve the previous equation of motion entirely separately for the pressure and velocity using the boundary condition as first solid surface, so boundary for solid surface. Let me write first inlet and outlet flow. We have a function, for example, for velocity and P are noun. There are also some boundary condition in the solid interface and also gas interface related to the free surface which P equals to PA and later, usually in another course, we can solve for temperature distribution from the equation of energy, which depends on velocity v through the dissipation v, and the total time derivation operates d on dt. Inviscid flow approximation also have the subsection in this chapter. Inviscid flow in the later chapter, assume inviscid flow throughout, for which the viscosity mu equals to 0. Thus, momentum equation reduces to, in this case we have mu equals to 0. Momentum equation reduces to which called Euler Equation.